All right, so today we begin our third topic of our course, which is microprocessors. And we'll see how the concept of microprocessor evolves from what we've been discussing so far regarding the register transfer level description of a digital system. So we've been looking at these examples of addition and subtraction. And so what, if let's say for some reason a person wanted a dedicated IC which would perform this particular function here, which would take these numbers. So we have a dedicated IC here. Let's say A, B, C, D are the four inputs that are there. Y is the output. And for the sake of discussion, let's assume that each one of them is 4 bits. A is 4 bits, B is 4 bits, and so on and so forth. The output then, we may have to allocate about 6 bits. Because it's addition of 4-bit numbers, we may have to allocate 6 bits here. So 4 into 4, 16 pins would be required in an IC to input these particular numbers. 16 plus 6 here, which is 22. Our IC will have to be powered by a VDD, 23. Ground has to be there, 24. Clock has to be there. It's a synchronous system, 25. And a reset pin we'll have to provide, we have seen. So that brings us to 26 or so. So the simple IC that we have to design is a 26-pin IC. All right? Now, as I said, finally, this IC is going to be implemented on a piece of silicon. And this is where our IC is going to be. This is where our IC is going to be. All the gates and all that you've seen, registers, controllers, everything would be here. And what you see here is that it's surrounded by what we call as pads. It's surrounded by pads. These are what? These are big pieces of metal deposited on silicon dioxide. The dimension of these pads, they vary. And for our discussion for 0.18 micron, we'll take, this is what is called as the pad ring. We'll take the dimension as 70 micron. So each pad that you see is a piece of metal deposited on silicon dioxide. Is 70 micron here. So 70 into, if we design it as a square, so you see here 70 into 3. So we'll take it 50, fine. So to get the numbers right, we'll take it as 50. It could be 70 also. So we'll take it as 50. So 50 into 7 gives us 350 micron here. So what you see here is we have 7 here, and we have basically a 28-pin IC. 28-pin packages are available. So packages don't come in odd numbers. You can't go and buy a package maybe which gives you 13 pins or 23 pins and all that. Packages have been designed of certain sizes here. So 28-pin packages available. So we could take our IC here, whatever IC we are designing, we could try and fit it into this 28-pin package here. So if you're wondering what is this pad ring, so our IC is going to be here. Our IC is going to be here, right? Our IC is going to be here. And, in our IC, let's say there's a register here, all kinds of things may be there. So eventually what happens is this IC, these registers that you see here, they are all connected here to these pads here. It may be connected to this pad here, this may be connected to a pad here, this may be connected to a pad here, right? So all the connections that you want to bring it out into the external world, they're all connected to the pads here, these metal pads here. And to the metal pads, eventually a wire comes in and attaches to this thing and eventually goes to the pin of the IC. Pin of the IC. Right? So you have a small silicon die. The silicon die is surrounded by pads. All the connections are brought to the pads. And from the pads, you may have a wire here which connects it to the pin of the eventual pin of the IC. Okay, so that's the arrangement that we have. And so if we look at this one, so we require a 26-pin IC for our simple example. And we have a 28-pin package available to us. And what we are seeing is that then what we have is each pad is 50 micron by 50 micron. So we have available inside the silicon, we have available 350 micron by 350 micron. Area is available for us to accommodate our circuit. Whatever circuit we are designing, we have to accommodate in that particular area, okay? So because our circuit is fairly simple, so we can do a bit of calculation and understand, is this area too big, too small, where are we in terms of the area here? So this is an example of a early Intel 80286 microprocessor. 286 microprocessor. So you can see there are lots of things here, registers and all that. We'll see a simple microprocessor, but note that if you can see here, these are all surrounded by pads here. If you can note, surrounded by pads here, all around you can see pads here. And connected to the pads are these wires. These wires that you see here, the wires are attached to these pads, and wires will eventually go to the pin of the package, and that's how you have the final IC, okay? So you can see that particular picture. So this is what we are also talking about. This is the space that we have available, surrounded by pads here, and pads will be connected to the pins of the IC here. All right? Okay, so this is the design that we have. We have looked at it, AB plus CD and all that, so we have this particular design. One particular implementation was here. So from the information that I was giving you for 0.18 micron technology, I showed you earlier one flip-flop. I showed you how much area and all that it takes here. So using that, a 4-bit register, one flip-flop is 75 micron square area. One register, if we multiply it by 4 of them, so it gives us a 300 micron square. Okay? 300 micron square is the area occupied by a register. 4-bit adder, similarly, I go into that library, and 1-bit adder area is given, and then I simply multiply it by 4. So 4-bit adder is 600 micron square. There is a 2:1 mux here. 2:1 mux is about 100 micron square. 4:1 mux also we require here, so it's 260 micron square. So we add them up. It adds up to about 2760 micron square. And note that the eventual area occupied would be not just the blocks, but we need area for wiring also. So just to make it, we don't have an estimate of wiring area right now, so we put some number here just to make it another 1,000 or so micron square for wiring, so it comes out to be 3,600 micron square here. All right. So basically, the chip area then is don't take the numbers. The numbers can vary. We don't have wiring area and all that is not there. So don't take the numbers. It may be 3,500, it may be 3,400 or whatever. So that doesn't matter. So chip area then is about 60 micron into 60 micron. If we design it as a square, it's 60 micron by 60 micron. And remember the core area, the area where we have to fit in our IC, was 350 micron by 350 micron here. So chip area is 60 micron by 60 micron. Core area is 350 micron by 350 micron, right? And you require eventually 26 pins. Why are we using such a large core area, 350 micron by 350 micron? Because the number of pins is 26. And each pin is requires a pad of 50 micron by 50 micron. So I'm forced to use an area of 350 micron by 350 micron. My IC is only 60 micron by 60 micron, right? So these kinds of ICs are called, they are basically pad limited. They are pad in terms of area. It's not the chip area which is deciding how big is your IC, what is the area occupied by the IC, it's the number of pins which is deciding. The number of pins that you have is deciding the total number of pads that you require, and that is deciding the eventual area here. So we call such ICs as pad limited ICs here, pin limited ICs or pad limited ICs, because the area is decided by that. Your chip is going to be, if you draw on scale 350 micron by 350 micron, you see your chip here, chip would be something very, very small sitting here. So at this stage, you may start to wonder that I require 60 micron by 60 micron area. And because of the number of pins, I'm using 350 micron by 350 micron. Remember, the size translates into cost. The larger the size, the more the cost that you have. So at this stage, you may begin to wonder, can I reduce the number of pins? Right? So note that what we are doing here is we are feeding all the inputs in parallel. We are feeding all the inputs in parallel. At this stage, you may conceptualize, why don't I feed the inputs serially? First, I feed in A. Then the same set of inputs, I use it to feed in B. Then same set of inputs, I use it to feed C and D serially. Now what would happen is, as you feed in serially, you would require more clock cycles. to read the data. Earlier you could read A, B, C, D all simultaneously. Now you will require 4 clock cycles to read all the particular data here. But then if you do that and we recalculate, this we were doing it in parallel. But if you do this, if you are willing to pay some price for it, then note that the number of pins would reduce to 4 here, and 6 here, 6 and 4, 10, 11, 12, 13, 14. Right, 14 pin. And 14 pin packages are available. So that would result in 14 pin or 16 pin IC, let's say if I use. And 16 pin IC, the core area is 200 micron by 200 micron. I have 4 here, 4 here, 4 here, 4 here. So we have 200 micron by 200 micron. Still is larger than what we require. We require only 60 micron by 60 micron here, right? So we still require a smaller area. But this is better than the earlier 350 micron by 350 micron. You're saving area and thereby you're saving the cost here. So what I'm trying to illustrate is how you conceptualize your IC. When you're defining your IC, am I going to feed in parallel? Am I going to feed it in serial? When you're conceptualizing your IC, you have to look at eventually how many pins do I require? What is the eventual area that my IC would require? We have to pay attention to all of those, and that would eventually, all those considerations would eventually decide how do I think about my IC? Should I feed in parallel? Should I feed in serial? Can I tolerate the delays associated with it? So those issues will come in to decide, how you think about your IC, how many pins. So number of pins becomes very critical. It's not, you can see, it's not that you can have as many pins as you want. The pins eventually translate into the area and the cost. And remember also, a larger pin package will cost you more. A 16 pin package will be cheaper compared to a 28 pin package. So you'll have to pay more. So anyway, so those considerations will come into picture. But let's come to our main topic here. So we've been talking about basically a digital system for the sake of convenience and simplicity. We've been talking about a digital system where we are adding, subtracting, multiplying, and things like that. All right. So if we're talking about basically an adder subtractor IC here. So now, so we just showed you that an IC like this would occupy 60 micron by 60 micron and so many pins and all that, right? The issue is, can I afford such an IC? Suppose I could design, right? I mean, you could, somebody wants to add up 4 numbers for whatever reason, A plus B plus C plus D wants to add up 4 numbers, wants a dedicated IC, which we call as a custom designed IC. Dedicated IC means, let's say a dedicated IC which will do that. The issue is, can you afford it? Okay, so what do I mean by that? Let's say another person, he wants to do this, A plus B plus C minus D, and wants a dedicated IC for that, right? A third person, she wants to do this, A plus B minus C minus D minus C. Now, it all seems ridiculous, but the point is that different people may want different ICs with different functionalities. Here in the context of adder subtractor, we are saying this person wants to do all addition, this person wants to do one subtraction also. Here there are 2 adders and 3 subtractors. Can each person afford a dedicated IC? Okay, so that's the issue that we are raising. So remember, when we talk about whether you can afford means, will the IC be economical? Will it be of a cost low enough so that it makes sense? So we said earlier, as a very simple cost model, we have cost of an IC is made up of 2 parts. There is what we call as the production cost. Each IC takes up some silicon area, takes up a package, you have to put it in a package, there's a testing cost. So each IC has certain cost of producing it. And then there is a development cost. There's a development cost which is shared amongst all the ICs that I will eventually sell over the lifetime of that particular product. All the ICs that I will sell. Because the development cost is what we have is what we call as a non-recurring cost, is a one-time cost. One-time cost, while this one is a continuous cost. As many ICs you have to produce, that much cost you incur here. So let's look at this particular part here. The production cost, we had seen earlier in the very beginning. Production cost is related to the area of the IC, the die area. The die area will decide, that's one cost. The packaging cost, and then of course there's the testing cost. Okay, so these will be determined by these 3 main components here. Let's look at the first one here. The development cost is made up of two major factors here. One is what we call as the mask cost. And the other one, but before the mask cost, there is a design cost. There's a design cost and then there is a mask cost. I'll explain what is the mask cost in a minute here. So design cost is easier to understand. We've been saying that all these designs, but in this case, of course, you could do it by hand and all that. It's simple enough, but most of the time, the design is complex, so you have to use a series of CAD tools. These CAD tools are very expensive. There's a license fee that has to be paid. So when you're engaging a CAD tool to do your design, in some sense, you're paying a cost. So that's one major cost factor, which is the use of the design tools that are there. The other one is you need expertise to do the design, so you have to hire engineers. And you have to hire engineers. Let's say you have a 3 to 4 member design team, and the design team is working for 6 months, you have to pay their salaries. And not only the engineer salaries, remember there's a lot of other support staff and all that is also there, right? So you have to pay salaries and all that. So what I've put here is a 100,000 design cost, okay? 100,000 design cost, you think about 3 engineers, well, maybe 3 engineers working on this design. The point is not to take it too seriously, but 100K is a reasonable cost for a small IC, okay? 100K is a cost here. What is this mask cost? Okay, so let me explain this mask cost here before that. So mask cost, if you realize what we are making is a CMOS IC. And CMOS IC is made up of transistors. Obviously N-type transistors and P-type transistors. And if you recall, if I can just sketch a simple transistor here, note that the transistor is like this. N plus, NMOS is N plus here. Just to recall, there's an oxide here. There may be a metal, polysilicon here, and contacts here, and all that, okay? So you see that the MOSFET is here. MOSFET requires an N plus region. Okay, I'm not going into the full, we'll come to the full fabrication of a MOSFET and circuits later on. It requires an N plus region here. Now, which is what's shown here, that you require an N plus region here. To create a MOSFET, you have to make an N plus source. You'll have to make an N plus drain. So let's say, in the piece of silicon, you want to create an N plus region here. Now, you will obviously create an N plus region only where you want the source. So it's not created everywhere, right? N plus region would be there at selective places. So the issue is, how do you create that N plus region? You're given a silicon wafer, and you want an N plus region which will act as a source for MOSFET number 1. So how do you create that N plus region here? So let me show you in very simple form, how do you create this? So what you do is, you take your silicon, you cover it with silicon dioxide. You cover it with silicon dioxide. After that, what you do is you cover it with photoresist. Photoresist is a polymer which is sensitive to light, right? So you cover it with photoresist. So if you expose it to light, its property changes, and the part which is not exposed, its property remains the same, okay? So the next thing is, we use a mask. So we have silicon, we have coated it with silicon dioxide, and we have put photoresist on top. And then we put a mask here. So mask, in simple terms, you could think of mask, let's say, as a glass plate with some regions which are opaque and some regions which are transparent. Okay? Some regions are opaque and some regions are transparent. Now what you do is, you expose it here to ultraviolet light here. UV light here. UV light expose all over. Right? Expose all over. So what would happen is, as you can see here, the UV light would then go here, right? UV light would go here in this particular region. The opaque region blocks it. So what happens is, this part of the photoresist, if you look at this part of the photoresist here, this part of the photoresist is exposed. This part of the photoresist gets exposed. The remaining part is not exposed, right? So we have two different materials here. The one which is exposed has a different property, and the one which is not exposed has a different property. Now what you do is, you put it in a solvent, and what happens is the exposed portion is removed. The exposed portion is removed, and then what you do is you remove the other portion. You can put it in a hydrofluoric acid, you know, HF. HF will etch away silicon dioxide. So you etch away the silicon dioxide here, right? And after that, you can remove this particular part here also. All right, so anyway, so you're left with this part here. Now what you do is you do a diffusion. For example, you want an N+, so you diffuse, say, phosphorus or arsenic into it, or you ion implant it. So you diffuse or ion implant it, and you end up getting a N+ region here. So you saw a series of steps which were involved in creating a N+ region in a piece of silicon, right? Now, all these steps that you're seeing here, putting silicon dioxide, putting a photoresist, exposing it, these are what we call as different process steps. So that, a foundry, wherever these things are manufactured, a foundry, an engineer there would, or their team would know how to do an SiO2 deposition, how to do photoresist deposition, how to expose it, and things like that. All these things, they're process engineers, they know how to do all of that. But what they don't know is, where do you want this N+? That they don't know. That information you as a designer have to supply. That I want a MOSFET at this particular place in my IC, and at that particular place I require an N+, and so you have to supply that information, that I want an N+ here. So eventually, who decides that I want an N+ at that particular region? Is the mask. All the other steps are generic in nature. The mask will decide where do you want an N+ region here. Which region is opaque and which region is transparent. So the mask decides where you are going to create an N+ region here. So the design that you do, eventually your design is translated into what? A set of masks. A set of masks decide where the transistors are made, where they are interconnected. All the information about your design is eventually translated into a set of masks. And these masks are, what we are saying is, they are expensive. The masks may cost you $100,000. In fact, let me show you some numbers for the mask here. Actual numbers here. Here. These are taken from a particular source. These are the mask set cost for different technologies. For a 180 nanometer technology, you can see somewhere in the middle, this is 200,000, 400,000, and like that. Here is the 1 million mark. 1 million and all that here. So this is roughly lies around, halfway mark here, about 100,000 or so. So there are, for your complete fabrication of the IC, something like 20 to 25 masks may be required. 20 to 25 masks may be required, and the whole mask set may cost you, as you can see here, 180 nanometer, it may cost you $100,000. And you can also see here, if you go to 28 nanometer, it may cost you $1.5 million. The mask cost.
So isn't this on an area basis?
No.
So what is producing one mask regardless of the area cost?
So for your IC, right? So remember, the IC may be small, but what is fabricated is a complete wafer, right? So you'll make multiple ICs here. So your mask covers the entire wafer, right? So you're using up the entire, okay, in a normal process. Okay. Of course, there's a possibility of, in a particular wafer, we may fabricate your ICs and his ICs and all that also. We can share it. Then the mask cost can come down. We could share that. But, those things will come to later. So please note that the mask costs are very, very high.
So what is it?
We'll not go into that. As I said, how the masks are made and all that, take it as a homework assignment, read it on your own. We'll not go into the details of the fab process here. But the masks are very, very expensive. The cost of producing all the masks that you see here. Okay? Which means that, come back to your IC economics. So $100,000 is taking you to, by the way, if you're thinking $100,000 design cost is very high, it's not. The CAD tools that we have, the license fee for some of these CAD tools can run into also millions. License fee for these CAD tools. You will use not just one CAD tool, you use a whole set of tools, right? So the CAD tools are expensive. And the salaries, all of you want good salaries, so salaries are also not very, especially when the expertise is high, the salaries are also very distinct. Yeah. Anyway, so suppose we do take this development cost as $200. And now the problem is, you want this particular IC, and you want only 1,000 pieces. You want only 1,000 pieces, right? For whatever small application that you have, you want 1,000 pieces. Development cost is $200K divided by 1,000, and the first cost itself comes out to be $200. You won't want a $200 IC which does this, right? It's simply uneconomical. What does it mean? It means that you cannot have a custom IC. An IC design customized for your application. You can't afford it. It's not possible. On the other hand, you can immediately see that if I have an application where N is 1 million here, then this particular cost comes out to be $0.2. Then this cost becomes small. And then maybe, if you're talking about 1 million or more volume, then yes, maybe a custom IC can be designed for you, right? But if your volumes are small, the thing is you cannot afford it. You cannot design a custom IC, even though technically, yes, you can do it, but economically it doesn't make sense. You cannot afford it, this thing here. So now the issue for us is, somebody wants an IC for this application, 1,000 pieces. Another wants a IC for this, which is 1,000 pieces. Another one wants an IC for this 1,000 pieces. What does that person do? You cannot have a dedicated IC, you agree? Now what does that person do? No, so one option is the person goes and does a PCB, right? The person goes and designs a PCB and takes multiple ICs and connects them up, right? Connects them up and makes his, so for example, for implementing a system like this, you require adders, subtractors, controllers and all that. You can get off-the-shelf ICs. There's an adder IC available. There's a register IC available. There are muxes available. You can take all these ICs, connect them up on a PCB and make your design. That you could do. But what is the price that you have to pay? The area becomes larger. The power becomes, it dissipates more power. Now note that on a PCB, the wire lengths are longer. It becomes slower. And not only that, in a PCB, your design is visible to everybody. They can know that you are trying to add 4 numbers, A plus B plus C plus D. So your design is revealed to them, right? So you don't have secrecy. You cannot protect your design. It's visible to everybody. They can reverse engineer and make another PCB and sell it for lower cost. So it's hard to protect your design. So you have all these problems with the PCB, right? You can go to that particular route. PCB route is there, available. But you don't want to go to a PCB route for your very innovative design. You want to protect it, right? And you want it to be small and for whatever reason, maybe you're sending this particular IC into space, into a satellite, right? Into a satellite, and weight is a big problem for you. Weight and all that is a big problem, so you would want it to fit into, as compact as possible, right? So you want a single IC solution. Right? As I said, you're not happy with PCB. That's why you were thinking of a custom design. So you want a single IC solution. So what do? You want a single IC solution, but you can't afford a custom design. Right? So this one possible solution to this is, so as I said, large number of users are there, each demanding custom IC solutions, but in low volumes here. So one of the solutions is we design a general purpose digital IC. A general purpose digital IC, which each user can customize for his or her application. So that's the approach. You want a custom solution. You can't afford a custom design and fabrication. So we make available a general purpose IC which you can customize. Now, have you seen this before? Huh? Well, let's come back to your EE210. Have you seen this before? This approach. Have you seen an approach like this? Yeah, look at this one. All right, let's come back here. Example from the analog world, right? So one person requires an amplifier. You design an amplifier like this. This is good enough, maybe a gain of 20, 25. You are all doing in 380 now, an amplifier like this. Another person requires a different kind of an amplifier, and you decide a cascode amplifier is required for that. So you design a cascode amplifier. The third one requires a different kind of an IC. You may think of, I need a differential pair and a multi-stage amplifier, right? Now note that different people have different requirements from an amplifier, and there are different solutions. This solution is optimal for one particular application, this is optimal for another, this is optimal for another. But remember, the expertise for designing all these amplifiers is not trivial. I'm sure all of you are a little bit struggling in your 380 lab. So expertise is not trivial, right? Expertise for designing these IC, especially now note that you're doing it on a breadboard. But if I were to tell you that design it on an IC, the complexity would increase exponentially. On a breadboard is relatively easy, but designing an IC which will do that will become much, much harder. Okay? So suppose we want all of these solutions, but these solutions we cannot afford it because it's too expensive. The design is too specific here. So people in the analog community, they came out, as somebody rightly said, with an idea that make a general purpose amplifier. Make a general purpose amplifier, which we call as an op-amp, which everybody, almost everybody, can customize it. So it's a general purpose IC. You want a gain of 20, well, you customize it by adding R1 and R2, and you get a gain of 20. Somebody wants a gain of 50, can customize it also to get a gain of 50. Right? So the solution is a general purpose IC, which can be, in some sense, if you note, which this IC, you are sort of programming it, right? You're programming it by what? By adding external R1 and R2 and all that. You can think of it as a way of programming your op-amp here, by adding some external inputs here, right? So you could do that. But note that for each application, maybe this is an overkill. This guy wants, look at the number of transistors here. There may be 24 or 25 transistors here. While, and this person wants a gain of only 20. You could do it with this application also. But then now you're doing it with 20. Yeah, there's economies of scale here. Because here, it's a one-time design cost. Now, to design an op-amp, you really need high expertise. You need high expertise and all that. So but it's a one-time cost. 741 op-amp, if you design, is a one-time cost. And I'm sure they have sold millions and millions of such 741 op-amps here. So that cost gets divided by hundreds of millions of ICs that you've sold, so the cost becomes negligible here. So eventually it translates into per IC cost here. So the point is that if you want a custom solution, a custom design and custom fabrication for you would usually be not feasible if your volumes are very low, which may happen in many of the cases. If the volumes are very high, yes, you go ahead and design a dedicated IC for your application here. So we come back. So what we are going to do is that for our example here, all these ICs that we required here, A plus B plus C plus D, A plus B minus C, what we are going to do is design a general purpose adder subtractor IC. A general purpose adder subtractor IC, and this general purpose adder subtractor IC will give it to each one of these people here. They'll customize it to do this or this or this or this. Right? So you still have one IC solution which will be customized for this one here. Now, because this is a general purpose adder subtractor IC, this person may require only 1,000 pieces. This will require 1,000 pieces, and this will require 1,000 pieces. And like that, if I have 1,000 other customers, I may reach a volume of 1 million, and therefore this IC can be a low-cost IC. Could be only a $1 or a $1.50 IC, which each one of them now can afford. Right? So the trend is that a complex IC to be useful, in general has to be made a general purpose IC which can be customized. So how do we do that? How do we construct an IC which can do this or this or this or any of those four let's say you have 4 numbers and you want to add or subtract 4 numbers, this IC will be able to do any 4 addition subtractions for you. Okay? How do we design that? So let's go into the idea behind this here. So this is our EE370A general purpose adder subtractor IC. All right? So that's what we're going to design. General purpose adder subtractor IC is there. So our IC is going to have, as usual, VDD and ground. We'll have a clock and reset. And let's work with 4-bit inputs, and we have an output here. So basically, so let me proceed with design of this particular IC. So what I'm going to have is, some choices will look a little bit arbitrary in the beginning. So I'm going to have in my IC, I'll have 4 registers. As you can imagine, I'm adding 4 numbers, right? A plus B plus C plus D and all that. So at least 4 registers. So I'm going to have 4 registers here. A, B, C, IR. Why IR, you will see in a minute. A different name here pops out. IR here. A, B, C, IR. And obviously, I'm designing an adder-subtractor IC, so I'll have 1 adder-subtractor block. I could use 2, but right now, let's just use 1 adder-subtractor block here. Okay. Now, the basic idea is the following. My IC, this is important, my IC here, I'm going to design it in such a way that it can execute some very simple operations. It can execute an operation like this, load A. You would see that immediately it makes sense. I have to read the data, right? Load A does what? It takes the data from the input and loads it in one of the registers, A. Or I could have an elementary operation, load B. It takes data X and copies it into B. And you would also appreciate that I may want to move data around in my system. So I can copy the contents of register A to C and B to C also. And I have an add. I can add the contents of A and B and put it in A. Or I could subtract the contents of B from A and put it in A. So my IC, I'm going to design it such that it's capable of executing these elementary operations. These elementary operations, load A, load B, move CA, these kinds of things, it should be capable of doing. Because eventually what the user will do is these are the operations that the IC can execute. The user would now use a mix of these elementary steps and do his or her task, with whichever addition, subtraction you want to do, will now be conceived in terms of a set of these particular instructions. Okay, so these are elementary steps, elementary instructions, if you would like, that my IC I would like to execute. And you would, from the choice that I put here, you can see that if I can do these things, in general, I may be able to add and subtract any numbers. Okay, if something is missing, we can add some more elementary instructions here. All right, so this is where we are. So now this is the IC that we would like to design. And so note, if you want to do this particular one, how would a user now make this IC perform this particular operation here? So these are the elementary steps that my IC can execute. So the user could do the following. Could first make the IC execute this instruction, load A, then load B, then add AB, then load B, add AB, then load B, add AB, and finally move A to C. And you will see that the output is available in C. So this operation here, y equal to A plus B plus C plus D, can be executed by asking this particular IC to execute these elementary operations. Load A, load B, add A, B, and then your A plus B plus C plus D. So that's how you customize. So if your IC is capable of executing these elementary operations, then you can make this IC execute this part here. And similarly, you could make it execute A plus B minus C or A plus whatever you can think of. You could do all of that here. All right, so let's proceed forward. Now, each one of these elementary operations that you see here, load A. Now, for it to be, for my IC to do anything inside the IC, everything has to be represented in a binary form. Right? All addition, all numbers, everything, you know that it has to be represented. So let's say when you want your IC to do this operation, load A, this operation we will assign a code 0001. Because for example, how does the external world tell this IC to execute load A? How will it tell? Well, it will place, let's say on X, 0001. Then my IC knows, oh, it's 0001, which means I have to load A. Right? So the IC has to recognize whether I have to do load A or load B or whatever this one. So it has to do that recognition on the basis of some code. And these are the codes, let's say, that we assign, 001, 0010, like here. Right? Okay. So I could think of a scheme like this. Note that this is what we wanted to do, A plus B plus C plus D. We said a sort of a program, if you would like, now load A, load B and all that, a program like this would execute this particular operation here. Now this one, load A, load B, this whole thing could be described in this form. So the input that I give at X could be 0001, right? 0001, which means this one here. So my IC has to recognize. So first one, what it does is, suppose I design my IC in a way that the first input that comes in, it takes it as a sort of an instruction. Is this a load A instruction? Is it a load B? Is it move? Is it what? It takes it as an instruction. The second piece of data, second piece of information that comes in is the data. So first input is an instruction. What does the IC has to know what to do? So the first one is an instruction. The second one is a data, right? So load A, so it says 0001. And then in the next one, the next clock cycle, it sends the data. So this IC will recognize when it gets 0001, it recognizes that it has to load the register A, and so on the next clock cycle, it loads this particular data. Then it comes 0010. So it recognizes that it has to load it into B. Then I give a data again. So my data X that you see here, I've just decided that I'm going to give the data like the first input is going to be instruction, data, instruction, data, instruction. Now note that 0101. 0101 is what? Add. Now there's no data after it. But just to maintain simplicity, 0101, the next one, I just put a blank. Just to keep things simple, okay? I keep it blank. So no data is required, fine. It goes to the next clock cycle, ignores it. No data is required. Then it comes here, 0010, there's a data here, 0101, again it's an add. Well, I give a blank here. So like that, I give an input. I give an input like this here, X here. With clock cycle, these are the inputs that are coming. And you can see here, if I can do that, and my IC is capable of executing each one of them, then it will eventually do all this operation, y equal to A plus B plus C. Now, the issue is fine, so I'm going to give input like this. What does my IC look like inside? Okay, so what do we do? So this is what we want to do here. Well, we could have an ASM chart like this. Note that there is an instruction, there's a data. Instruction, data, that's how it is coming. So in state S0, what am I expecting? Instruction. First byte is an instruction. That's why I had a register called instruction register, IR. So the first one is read X. X is read, but I interpret it as an IR here. Then I go to S1 and I check IR. I check IR. Now IR is what? I check the code. 0001, it checks whether it's 001, 0010. So depending on the code here, it will cause A equal to data here, it will cause A equal to A plus B, C equal to, it will cause all these operations to occur. Depending on the nature of the code here, IR code here. It will cause either this to occur in my data path or this to occur in my data path. So it will send appropriate control signals will be sent to the data path to cause these things to occur. So you can see a simple machine like this here. Simple machine with S0, IR equal to X I read here, S1 here, and then we read data here. Should be able to execute this kind of a thing. All right, so let's proceed with this. Well, I can map it into a data path like this here. Now, a little bit of this thing here. So if I want to map it onto a data path, one thing is clear, I need A, B, C, IR. So 4 registers are there, A, B, C, IR. I need an adder subtractor block, so the adder subtractor block is there also. I've added a control signal here. Control signal will decide whether it does an addition or subtraction. Now, to do all of these operations, whether whether I go, in order to transfer A to C, to transfer the contents from A to C, what do you have to do? A wire has to run from A to C. Right? I mean, if you have to do A to C, you will eventually require this wire, let's say here, this wire run all the way here, right, to the input of this. Right? A wire has to run from A to C. If you want to move from B to C, then a wire has to go from B to C also. B to C also. Now the thing is, you can't run wires, whatever you want to do, you can't run wires between, dedicated set of wires between the blocks. You can't do that. As things become complex, if it's simple, fine, you can have dedicated wires. If you want to transfer from A to B, you can have a dedicated wire from A to B. But if you have lots of these operations that are going on, you can't have dedicated wires between each block. So what we do is, in order to avoid all of that, what we do is we define what we call as a data bus. A data bus is nothing but a set of wires that you see here in red. We define it as a data bus here, which runs through your system. So any time you want to transfer between any of these things, suppose I want to transfer from A to B. Now note that each one of these registers has a load signal and also has a sort of enable signal here. So load is understood, we have done that. Enable, when you enable it, then only the register will put its output on this particular data bus. Otherwise, the register is sort of disconnected from the data bus. How do we do that? It's very simple. We can use a tri-state buffers. A normal buffer is what? Whatever input is there, the output is also that particular y equal to A. But a tri-state buffer is that when it has an enable signal, and when enable equal to 0, in effect the output is open circuit. The output is open circuit, which means output is disconnected from A. When enable equal to 1, then of course y equal to A. So we can use these tri-state buffers that you see here at the outputs of these registers here, so that only when I enable this particular register, then only it gets connected to the data bus. So now all transfer, everything occurs via the data bus. The red line, the red set of wires that you see here, I have one set of wires running through my system. And if A wants to transfer something to B, what A would do is I would enable it, it would put its data on the data bus, it will come here, and then B, we will enable the load signal of the B, and when the clock edge comes, the data will be lashed into B. If you want to transfer from A to C here, well, I will again cause A to put its data out on the data bus. Data bus is running throughout my system, so it's available to C also. I will then enable the load signal, and the data will be loaded in C. So in all these complex systems, we don't have dedicated wires running. You can't do that, you can't afford it. Otherwise, it would require too much wiring area. So what you have is a single set of wires running, which is called the data bus here. You can here. So this is, now you can see here, all I require is A, B, C, and D, a data bus running through my system, an adder subtractor block, and we put a buffer here, tri-state buffer here, and with this system, I could execute these things here. I have to design a controller, but this data path can execute all of this here. If you want IR equal to X, what do you have to do? Well, you have to enable the signal here. You have to enable the signal here. Note that when we enable it, X will be available on the bus here, data bus here. So X will get connected to the data bus, and IR, and I will enable the load signal of the IR here. So when the clock edge comes, this X is available on the data bus, and when the clock edge comes, it will get loaded into the register. X will get loaded into IR. IR is, we have allocated note that what we are giving at the input is a instruction and a data, right? So within IR, we load a register, the first one. We load the instruction. And then it goes to the next state and reads the data here. In the next state, the data is read. Then when it comes again, it comes back to S0 and reads the instruction again. So it reads an instruction, reads the data, reads an instruction, reads the data, keeps on doing it, right? And that way, if you give X in a proper order, then it will execute this X that you see here. Your system will execute it and will cause it to do A plus B plus C plus D. So how are you customizing it? You're customizing it by writing this particular code here. And this code that you see here is nothing but a simple program. You're writing a program, right? A program consists of what? A program consists of instructions and data. So this is what it is, a program. This is a program that you're writing. And you're feeding the program at this point. And the program and your IC is general purpose adder subtractor IC is executing this. So in a way, what we have done is, we have arrived at, now you may feel, how do I feed in this particular data X here? I'm not sitting there and feeding in, note that this data has to go at a clock rate, right? How do I feed in 001 data, 0010, how do I feed it in? And it has to go at a clock rate. Clock rate is a megahertz. I can't do that manually, right? So it makes sense that what I would do is I have externally a set of registers. Externally, I have a set of registers, and I load my program into these registers here. So beforehand, whatever program I have, I load it into this particular register, and now the data actually comes from this set of registers here. Now from which register will it come? Well, when you have a set of registers, let's say you have 16 registers, I require an address. Which register is going to give the data here? Address. So I need a sort of address here, and who decides the address? Well, my 370A will send the address here. Will send the address here, this IC will send the address here, and depending on the address, the data is read from here or here or here. So what I do is I have a set of registers, and in that registers I load my program. Okay, and the data will come from here. Now I have to modify my IC also. So now note that my IC has to generate a register address also. So I'll modify it so that now it will be able to handle this. And now you're seeing what it is evolving into. A set of registers will become a memory. A set of registers will become a memory, and this one, it can do not just adder subtractor, but it can do all kinds of logical operations, multiplication or so. So it becomes a programmable digital system. So it becomes a microprocessor. So whole thing is evolving towards a microprocessor here and a memory here. So that's what a general purpose digital system is. A processor connected to a memory. That's what it evolves into. Okay. All right, so let's stop here, and I just wanted to, before we leave, just wanted to show you this picture of a data bus. This is a early microprocessor about which we'll spend a little bit time. 8085 microprocessor. So there is an arithmetic logic unit, ALU, there's an instruction register, there's a set of internal registers, register file. This is your finite state machine control logic here, and you see a data bus. See, in blue, you see this data bus running all through the system. And in green, I've highlighted here, this is the address bus that is going here. And these are the major blocks in your microprocessor here. Okay, all right, so let's stop here.